Hi everyone. I wanted to work through the solution to number 4 from worksheet 4.5 because it's a different kind of problem than those we've done so far. It's fundamentally a two-dimensional problem, and all of the problems we've done so far are really one-dimensional problems, or sometimes a couple of one-dimensional problems smushed together. But this is one where you really have to think hard about your coordinate system, and you actually have to treat the forces as vectors and split them into components. So what I want to do to set up the problem and show you why it's hard is draw a free body diagram on the stapler here. So the setup of the problem is there's a stapler on a book. The book is tilted up on a tabletop, like shown. There's some angle that the book makes with the tabletop. We're calling that angle theta here. And we're leaving it as an arbitrary angle to start. So it can just be theta, and we'll change it as we figure out more, or we'll plug in a value as we know more. But the stapler does not move at all until theta gets to 37 degrees, and then it starts to slip. So static friction holds the stapler there until theta is 37 degrees, and then static friction isn't strong enough to hold the stapler, and the stapler starts sliding. Okay, so I want to draw a free body diagram for the stapler right before it starts sliding. So that is right at that threshold value. So that is when theta equals 37 degrees. So I'm going to draw my free body diagram down here. I'm going to draw the system again. So here's my book. I'm just going to draw it kind of simplified. So there's a book. That's my stapler. This is a stapler, as you can tell from the diagram. So we're right at this threshold here, 37 degrees. The forces that are acting on the stapler, there's 3 of them. There's gravity. So that is the mass of the stapler times gravity. There's also a normal force preventing the stapler from falling into the book. And it's a normal force, so that means it points normal to the surfaces that are in contact. In that case, that means that it's pointing perpendicular to the surface of the book. That's the normal force that the book exerts on the stapler. And then there's also a static frictional force that prevents gravity from pulling the stapler down the incline. So that points this way, along the incline, and I'll call that F sub S. So we know that our model of static friction is that this value has to always be less than mu s times n. So the normal force here represents the normal force between the stapler and the book. And we'll have to figure out what that is to really use static friction. But we know at 37 degrees, that's right when the book starts to slip. So that's right when static friction is overcome. So we know right before it slipped, the static friction had to be equal to its maximum value. And after that, it couldn't hold the stapler in place anymore. So as the incline got larger and it got harder to hold the stapler in place, the force of static friction increased to just match whatever force was pulling the stapler down the incline, until we got to this threshold value where static friction could just barely hold it using its maximum value, and then it couldn't hold it anymore. So this is, we're at the maximum value of static friction there. Okay, so that's one thing. But you'll notice that we have forces pointing in funny directions. There's not a clear X and Y. There's not a clear horizontal and vertical direction as there have been in other problems. And what I want to do is I want to establish a coordinate system based on something that makes sense for this problem. What I'm going to do is I'm going to say that this direction down the incline is X, and this direction perpendicular to the incline is Y. And what I'm going to do is I'm going to use Newton's laws, and I'm going to say that always I can use Newton's laws in two dimensions, Newton's second law. Newton's second law says that the force in the x direction, force the net force in the x direction will be equal to mass times acceleration in the x direction. And the net force in the y direction will be equal to the mass times acceleration in the y direction. This will always be true, always true, no matter what x and y I choose, as long as x and y are perpendicular to each other. The reason why I've chosen this x and y is it makes things a little bit simpler, and we'll see how later. You can choose x and y any way you want. You could choose your x and y to be conventional x and y, like you could choose this to be x and that to be y if you wanted. It will make the problem a little bit more complicated, and we'll see that later, but I'm choosing it to be like this. That's my x and my y. X points down the incline, y points perpendicular to the incline. Okay, so here's what we're doing. We're taking our forces and we're breaking those forces into components that point along either x or y. So what I want to do is I want to say that really, if I look at these forces, I've got a normal force. That normal force points exactly in the y direction. I've got a frictional force. That force points exactly in the negative x direction, but my gravitational force points partially in the x direction and partially in the negative y direction. And I need to understand how that works. What I need to do is I need to treat the force of gravity as the hypotenuse of a triangle and take the legs of the triangle to be the component of gravity that's in the x direction, that's that little dashed line, and the component of gravity that's in the y direction, that's that little dashed line. So this here will be mg in the x direction, and this here will be mg in the y direction. And I've got a little triangle. So if I have a little triangle, I need to do a little bit of trigonometry here. So here's a little geometrical argument for you. If I imagine extending this mg line down to the bottom here, that makes a right angle with the bottom. And in this triangle, I've got, maybe I should just redraw this triangle. So if I've got mg down, I've got the incline going this way here. So this angle is 37. That's a right angle. And I've got my, my components of gravity going like this. So that's my x component of gravity. And that's my y component of gravity right there. Right there. This angle is 53 degrees. Has to be, to make the interior angles equal to 180 for the entire big triangle. So this angle, and this angle have to be 180. This one's a right angle. So 37 plus 53 have to be 90. So I know this angle is 53. That means that I know that I've got a little triangle here. This angle then is theta, or 37 degrees, because that angle there, that's the 53-degree angle. This little angle right here, that's the 53-degree angle from this triangle. So this angle here is the same as the angle of incline of the book on the table. All right. So now I've got a triangle. I know the hypotenuse of the triangle. The hypotenuse of the triangle is mg. And now I can figure out what the components of gravity are in the x and y direction using the hypotenuse and the angle. So I know that, and let me write that out. So the force of gravity, oops, I'm calling this mg, the force of gravity in the x direction is equal to the hypotenuse, the total force, which is just mg, times the sine of 37. So I'm taking the I'm using sine because this is the opposite side of the triangle from 37. And then the force of gravity in the y direction, the magnitude of it, will be the hypotenuse times cosine of 37. So I'm taking the adjacent side of the triangle. So I'm getting cosine of 37 there. The direction of the x component of gravity is in the positive x direction, and the direction of the y component of gravity is in the negative y direction. So let's apply Newton's second law here. If I apply Newton's second law, then I can say that the net force in the x direction is equal to the mass of the stapler times the acceleration of the stapler in the x direction, which we'll come back to. And that's equal to the force in the positive x direction, which is mg sine 37, minus the force of friction, which is mu s times n at this angle. And we don't know what n is yet, so we need to figure that out. In the y direction, we have that m times the acceleration of the stapler in the y direction is equal to n, which is the force pushing the stapler off of the incline in the y direction, minus mg cos 37. Okay, well, one other thing we can say for sure is that this is right before the stapler starts to move. It's just at this threshold value where static friction is still just barely holding the stapler in place right before it slips. So that means that the acceleration of the stapler here is 0 in both the x direction and the y direction. It's not moving at all. It's not accelerating at all. That means that ax is 0 and ay is 0. So I can say that both of these equations are equal to 0. And if I look at the y equation, that says that n minus mg cos 37 is equal to 0. So the normal force here is actually equal to mg cos 37, not equal to the full weight. And the way to interpret that is when this book is at an incline, some of the weight goes to pulling the book down the incline. That's this part. So the full weight isn't being pushed into the book. So the book doesn't have to push back with the full weight. So that's this. We only get a fraction of the weight for the normal force here. Some component of the weight for the normal force. So if we know n now, we can go back to the x equation and look at what we get when we plug in n. So we know mg times sine 37 minus mu s times mg cos 37 equals 0. And now we know, we actually don't know the mass necessarily, but we can cancel the mass out. It ends up not mattering here. That's kind of nice. And now we know g. Let's approximate it as 10. And we can calculate sine 37 and cos 37 if we want. The only thing we don't know is mu s. So let's figure out what that would be if we solve for it. So we're going to get g sine 37, and then moving mu s g cos 37 to the other side, we get this. And then we divide by g cos 37. The g's cancel. And we get that mu s is equal to sine 37 over cos 37, which is equal to the tangent of 37 degrees. That's interesting. This number has nothing to do with gravity or the mass or anything except for the angle, which is kind of cool. So I'm going to leave part B as an exercise for you guys, but some of the same work with components will be really important for that problem too. But I just wanted to show you how you can break a force into components, establish a coordinate system that makes sense for your problem, and then work with it that way. So I hope that helps. We can definitely talk more about this in class because it's complicated and new. And I will see you soon. Bye.